Question and answer, chapter 14. What do you got?
Bulletin 14.4.
14.4.
It asks about whether it's differentiable.
Right.
And then we'll
This is 3, 4, 5, right? Sections 3, 4, and 5. Determine why the function is differential. So f of xy is differentiable at a point if. There's a theorem, actually states this. I think it's back 2 pages from where we are. It's one of the boxed-in theorems. A function is differentiable when the partial derivatives exist and are continuous near point A, B. At. And then I gave this a title. I said, this is what it means to be C1 function. To be continuous in the first derivative.
meaning they have the same value, but the derivatives have the same value.
I don't care about the numbers. I don't care about the numbers. I just care that the derivatives themselves are continuous. So for example, if we think of f of x equals ln of x, that's a perfectly differentiable function, right? But if I look at the derivative, f prime of x is 1 over x, that fails to exist at 0. Okay, it's continuous everywhere. Yes? Everywhere that this is continuous for all x not 0.
Yes.
This is only continuous when x is bigger than 0. So I have to look at what goes on in my partial derivatives. So the function in question, if I look at like 13, for comparison, 13 is x squared e to the y, right?
Yes.
Okay, so what's the partial with respect to x?
2x ey. And 1 6 squared.
Now, exponentials are continuous everywhere. Polynomials are continuous everywhere. The product of continuous functions is continuous. So these are continuous on all x and y. And that means that the original function is differentiable everywhere. Now, I think I see one of the problems. One of the problems is the way we're using the term. Back in Calc 1, I said a function was differentiable meant it had a derivative, right? Here, I've got partial derivatives. So when I use the term differentiable, what does that have to do with partial derivatives? There's no full derivative, right? I've got parts. But what I'm claiming is that these partials can be combined somehow to make one, quote, full derivative. But that's not really a topic for Calc 3. That's a topic beyond our calculus at the moment. But what that means is that this has derivatives because these things not only exist, they're continuous. It doesn't cause any more shears or rips or holes or differences from different directions, right? I still have all my continuity behaviors. Now, I think the function you're working with is a quotient, right? Which means you already know there's at least one place where it's not continuous, wherever the bottom is 0. And then they gave us a point, and in this problem, I think the point is 1, 0. But in this case, it's continuous everywhere. So I have to worry about that particular point. But in the other one, number 14, I might actually have to.
Like you said,
Because this is continuous everywhere.
Yeah.
I don't have anything to worry about, but I think yours is like 1 plus y over 1 plus x. Okay, what's the point in that question? What's the A, B they give us?
1 and 3.
Oh, well, the only place this is going to be borked is where x is -1. I don't have to worry about that. So hopefully, as long as I stay away from -1 for x, things should be safe. This is actually a connection I will make in complex variables next semester if you go to take that. In the complex variables course, we think of a function of one complex variable. But a complex variable is a real part and an imaginary part. It's an x and a y kind of glued together. Because we think of z well, then I take partial derivatives in x and y, but I take full derivatives in z. And that's really where this idea comes into play more tightly. There's a really tight connection between working in real variables and working in complex variables. I wonder you all look weird. I haven't put my glasses on. Okay, more questions. You're still looking at this kind of unhappy.
I just have so if you have the partial derivative of h, x, and y, and you plug in the points, do you expect them to be the same?
Nope. They could be completely different values. They could be the same. They don't have to be the same. Remember, we're looking at slopes in two different directions, right? The example we used, this one was 2, this one was 4. So it depends on the shape of the curve in 3D as to what those numbers will be in each direction. I mean, I could be going uphill in one direction and downhill in the other, but as long as they both work, it's okay. If either of these were not continuous functions, like here, I've got a 1 over 1 plus x, right? So that's not continuous at -1. So if somehow this point was related or in these derivatives, there were problems near this spot.
Is it like not continuous, just like at a point, like above, like 1 over x?
Sure.
That would make it non-different.
It would be differentiable away from that spot. So this function, the domain of this function excludes all the x values of -1. But we're looking at the point here, right? I'm far enough away from that line that I can say, oh, well, my discontinuities are way over there. In a small neighborhood, this is fine. Continuity is a local property. We all look at continuity near a point or near a section. Most of the time, we only say, oh, well, it's discontinuous over here, it's discontinuous over there. Everywhere else, it's fine. What that really means is in a neighborhood around each of those spots, I can make things work. And then even on the real line, we just looked at that epsilon and delta idea, right? So it was like in here, we're okay. There's a general idea in math. It works in most of calculus, it works in higher analysis, it works in a lot of other fields as well. That if you know what's going on in a small area, you can patch those small areas together to try and get a big picture. But it doesn't always work. There are cases where my patching together breaks in the long run. We'll see an example in chapter 16. More stuff. That's more stuff. Fourteen four 36. Wind chill. Oh, they're going to give me the equation. And it says then to use differentials, right? Okay. So the wind chill equation is 13.12 plus 0.6215T minus 11.37 e to the, v to the 0.16 plus 0.3965T v to the 0.16 again. Well, then that's just disgusting. Temperature is in Celsius, wind speed is in kilometers per hour. Wind speed is 26 with a possible error. Okay, wait a minute, right there. V has a possible error of plus or minus 2 kilometers an hour. And the temperature is given with a possible error of 1 degree Celsius. So we're also told the value. This was 26, this was negative 11. Right? Okay. What's the wind chill with these measurements? And then how far off could I be? Well, how far off I could be is dW. So I need to know the total differential of W. But now I get to say that I actually have a formula for this. We did dz in terms of x and y, right? So I go back and I say to myself, wait a minute, there was a formula. dz was partial z with respect to x times dx plus partial z with respect to y times dy. So in order to calculate dw, I do the partial of w with respect to t times dt, and then I do the partial of w with respect to v times dv. Oh, wait a minute, what's dt? There's dt. The possible change in temperature, right? And what's dv? There's dv. I don't know if you're going to do wind chill, but look at 38. .38 should look really familiar. That's the ideal gas law, PV equals nRT. Okay, if I change the volume by this much and I change the temperature by this much, what's the effective change in pressure? Or vice versa. Gee, I don't ever need to know that. You want to build anything that's going to work? Better?
Yeah.
Back in chapter 3, we would write, if we had y equals f of x, we would write dy is f prime of x dx. So all I've done is I've changed this to account for the fact that I have more variables. Kind of like my chain rule would go, right? From W, I have to go to T and V. So I got to use partials there, and then I have regular here. Yes, ma'am.
I would think that the T and V equations would be plus or minus.
I wouldn't. I'd just use the numbers. And then I'd say, oh, well, if there's a plus or minus in front of each of those, you put a plus or minus in front of the whole thing. Your wind chill could either be as high as or as low as. Just use 2 and 1. You still don't look like you're happy about that.
Like a derivative of it, it's 0, which is the number.
Oh, no, I'm sorry. Based on this, I would say dt equals 1. But that's this part.
We need it like.
No. And dv is 2. That's actually your adjustment, your little change in x, your little change in y.
I have a question with that. In 38, we have like an initial and final instead of just the change. So we can use the initial value in the equation.
Yes. You use the initials in the equation and you use the change from initial to final as your d. So I think it's like 12 to 12.3 for one of them.
Yeah.
So you use 12 in the equation and use the 0.3 as the change in. Remember, we're trying to do an approximation, right? So if I go with the nice number and then I move to the not nice number. I was kind of happy to see that 8.31 show up and I didn't have to remember what the molar constant R was. Because chemistry was like 40 years ago and I don't want to remember that. Oh, no. You're lying. Chemistry was only 35 years ago. More questions? Yes, me.
530, I just want to make sure that I'm doing it.
30.
4.530.
Yeah.
Because we got the equation that dy dx equals the negative of the partial derivative with respect to, or we get that like new equation, capital F, and
Yes.
then take the derivative with respect to x, and then over y, and I can just do that. I don't have to do anything else. Right?
Yes, you absolutely can go directly
We did it differently.
to this. Yeah, I know. But in order to use this, you have to put it all on one side, right? You have to have it equal to 0. So you've got to do that first. And then you can treat that whole thing as capital F. And then partial respect to y over partial respect to x, the minus sign. That absolutely works. But if that bothers you, you're welcome to do it with the chain rule with the partial of y with respect to x floating around in there. But that's why I thought working in partial derivatives makes it easier rather than having to do the chain rule version like we did back in chapter 3. So, yes. Whenever you have a function written implicitly like that, partial is the way to go. And as long as the bottom here isn't zero. I can't divide by zero. I suppose that would be really weird. If you had a function of x and y that only depended on y, then your original equation would have no x's in it. That would be strange. More questions?
You 14, 5, 9.
9.
I got confused with the tree and which part of the root is.
Sure. So this one says z equals ln 3x plus 2y. X equals y equals s sine t and t cosine s. Okay,
Like, you don't even have to do it, well, you don't have to write it all out, I just get confused, but I'll write it down.
right, there's my little tree. Now you tell me which derivative you want to do. That's a really bad looking z. Do you want to do the derivative in s or the derivative in t?
You have to do both.
Eventually, yes, but which one do you want to start with?
S.
Okay, so if I'm going to do partial of z with respect to s, start at z and draw all the branches that end at s. So I got to go this way from z to x to s, right?
Yeah.
So those are all branching. Yes, none of those are just one line. They're all splits, which means I got to use partials. So I'm going to go dz, dx, dx, ds, but those are all partials. And then I also have to get to this s down here. That means I got to go that way. And since I got to do both of them, I got to add them from z to y, from y to s. Now I haven't actually calculated any of the derivatives, but now I now know which ones I need to do.
And then you have to do t as well.
Yes, because it says in the instructions, it says find all the derivatives, right? Use the chain rule to find dx, ds, and dz dt. dz dx, dz ds, and dz dt. So it wants me to do them both.
Reading the question of 1 to 6, where it says
Ah.
dz dt, I was really confused, so that makes more sense. Okay.
Yes, especially if you notice that those are straight Ds, not curly Ds. That yeah, makes it very difficult. How am I supposed to do that with straight Ds? No, it's curlies. Partials. You'll notice though, even when I wrote it out, I said D
Yeah.
instead of saying partial, because it is really a derivative. It's really D. We're just writing it different to remind ourselves it is a different process. That is a recent change. The partial symbol being used this way is more recent. A lot of times they would just write the regular derivative d of the Leibniz notation the same way, and we would just have to deal with it. I think I got to go back and look in the history books, but I think this is a consequence out of, want to say Euler, and I'm not sure that's right. Lagrange, one of the French mathematicians. I'll blame it on all of them. Laplace, Lagrange, someone there in their study of thermodynamics. and mechanics in physics, because heat and motion in waves is both time dependent and position dependent. So the differential equations started to look different. And so they started to saying, wait, I really want to know what I'm taking my derivative in. And so instead of writing d squared u d squared dx squared plus d squared u dt squared equals 0, they said, wait a minute, that looks like they should be two separate u's, just a function of x and just a function of t. And I really want it to be one function of both. They changed the notation to use that. But that's the wave equation. The Laplacian is 0. There's one there's a different constant in here. I think it's alpha squared or something for the heat equation. But imagine a long, thin rod and put a heat source somewhere on it. There's my heat. This function is the temperature at some point x, assuming this is x equals 0, as time goes on. We lit the thing at time 0. So I think about it, well, the heat should grow here in the middle and should diminish as I go out, but over time it should increase, right? So over time, this will get larger and until the entire thing reaches a uniform heat. And it'll still probably be slightly cooler out here than it is in the middle, so there'll be a bell-shaped curve. All of a sudden, my statistics crap comes back into this. And this actually turns out to look like a normal distribution. In terms of a wave, hold down at one point, let it go, and then model the behavior along the string. This is exactly the same thing. We get position instead of heat. Okay, I just wandered way off, so bring us back to topic.
So, one of those cases, like, especially in 14.5, where you like.
Oh, yeah.
Like, partial, yeah, like.
That thing's going to end up in X and Y and T and S. Leave it that way.
Yeah.
Just leave it. We will find it is almost always easier to leave than it is to try and simplify that into all S's and T's. It's just too much of a pain in the neck, especially when we get more variables. As long as you can get all the right pieces in the right place there, I'm perfectly happy. It also turns out to be more useful that way in the long run.
So, like 18 trees and things again.
This.
Yeah.
Yeah, 18 just asks you to make a tree, right?
Oh, you don't have to write it out.
Use a tree diagram to write out the chain rule, yes.
Oh.
So once you've made the tree, write out these.
So would you get like DW, DU, WT?
Yes.
Is there any way of combining those, or are those like two separate?
No, they're completely separate. Just like I have DZ, DS here, and I'm gonna need DZ, DT separately from it. But remember that when we're changing, this part's gonna stay the same. Only this part is gonna change. This part's gonna stay the same, only this part's gonna change. So once you've written the first one, it's literally copy, paste, change 3 letters or 2 letters or whatever. It's much easier that way. Or it's be more things.
14. Number 62. I was just kind of confused on like kind of how to. Yeah, like I was confused.
Oh.
On the theorem thing.
Yes, so remember Clause's theorem. I think it's actually C2. Then my mixed partial derivatives. Partial with respect to x first, then y. And the partial with respect to y first, then x should be equal. So all you have to do is take the second derivatives and show that we actually get the same thing both ways. But it actually asks you in the problem to do all of the second derivatives, right? The problem, you said 13? No.
62.
62.
UXY
Equals UYX, yes. So it's, yeah, just take the second partials and show that they end up being equal. Now, notice this says nothing about UXX, nothing about UYY. Those are going to be completely different and probably different from this as well, but that's okay. Russell's equation. Wave equation. Oh, they didn't actually write down the heat equation. The only difference between the wave equation and the heat equation is the sign of this number. More questions? Yes.
68. But also very, the combination.
No, that's a third derivative.
So you take a third of each of them?
No. It's written, give them to me from left to right. It's partial third of V with respect to, which one's the left?
R.
And then T, right? But remember, we read these this way. So this is really the T first, then S, then R. So it's the partial derivative of the partial derivative of the partial derivative. So like a second derivative, when I write fxy, I'm really writing fxy. I'm doing the y derivative after I do the x derivative. So I can think of this as dv dt, and then I do the derivative with respect to s, and then I do the derivative with respect to r. See how we do them from inside out, and thus end up going from right to left in the bottom there?
Yes.
This is the operator notation. F of, right? F of x. The of is in the parentheses. Writing it like this makes it more confusing. I don't like it. But writing it like this, well, then it's T is the inside, so it makes more sense, right? So really, this is V TSR. I prefer the DDR notation, this one down here, because it function of, that makes sense. But now you also see why the cube here is on the D, right? Because it's D, 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 V. That's why the notation is weird. It's x squared on the bottom and it's D squared on the top. That's the way we write the derivative operator.
Or it doesn't matter.
by Clause's theorem, it will turn out that order doesn't matter, provided my function is continuous. You know this function is continuous? I don't know that to start, so I better not make the assumption.
So you go,
I go T, then S, then R. Or T, then S. I'm sorry?
did RST.
Ah, yeah, that's the problem. This, we have to go this way in, when it's written in the fraction like that. Well, you should check when you do it again. And maybe they do work out the same, but I don't know that to start with. And Clause's theorem should generalize, because Clause's theorem itself is only about second derivatives, and these are third derivatives. So I would actually need not only the first derivatives to be continuous, I need the second derivatives to be continuous. And then I need to be able to say, oh, well, then the thirds should match up right. But I have to check continuity for all those things, and we haven't yet.
Okay.
But that's our actual statement of the theorem up there. I need that extra continuity bit. I can take partial derivatives as far as I want in any of the variables. The question is the utility of what value is this particular third derivative. At the moment, I don't have one. I'm just practicing a skill. Take a derivative, now take another derivative, now take another derivative. Keep taking derivatives till you're blue in the face. Okay, now I know how to take a derivative. What am I going to use it for? Mixed third derivatives like this show up in weird places in both physics and in differential equations related to behaviors at boundaries. So to me, this screams a mixture problem over a semi-permeable membrane, which makes it pharmaceutical chemistry. It's been years, but that's the thing that jumps into my head. Oh, okay, I've got a motion of two different chemicals across a boundary with two different concentration layers. What's going on in what direction? Do I actually think I'm going to run into something like this? No, not outside a PhD program in chemistry. Where am I going to use this? Where are you going from here? More questions. I think I only have used a mixed third, like I think I used one mixed fourth once. And that was in a graduate course taught by Dr. Sparling, in a course well beyond anything we're ever going to get to here.
Like that one can be defined.
Okay. I am measuring the change in my function, right?
Yeah.
A derivative is a change in. So first I'm measuring the change in the t direction. Then I'm looking at, okay, now that's changing in S as well, right? And then that's changing again in R. So how do I look at the T change, then the S change, then the R change, one after the other?
These on. So this is my before.
Yeah, it is. V is a function of R, S, and T, right? So it itself is up here. And I'm looking at what happens when I change in the T direction. I get a new function now, right?
Yeah.
Of T, S, and R. Now let's change in the R direction. How does this thing change? Now let's change in the S direction. How does this thing change? Yes, I don't know how to draw the picture because it's four-dimensional. I'm not hallucinating enough. And that's the problem here. It's, what do you mean by this change? When I think of Z as a function of X and Y, well, I can think of, okay, I'm changing X. And then I'm changing Y. So I've got a curve with a slope in X, but now I'm going to measure how that changes as I go a little in the Y direction, right? So does it go up or does it go across? But it's not, when we did functions of one variable, it was like, okay, I got a tangent line and then I got concavity. But it's kind of like concavity, but I'm moving a whole curve. How does this curve change as I go in the other direction? So maybe my concave up, concave down idea works here. But there's got to be more to it. And then adding a third one. We didn't do third derivatives and their effects on graphs at all. So I'm not sure I have a good impact for what a third derivative might mean to a graph.
Right.
That's part of my problem. At least with first and second derivative, I kind of have that, okay, tangent line, concavity. But minimums, maximums, other things, right? There were other things. So I'll have to look at that as a separate example. But we didn't do third derivatives at all. And so that's my stretch here. How does my curviness change as I move along the, okay, wait a minute, curvy. We can measure curviness by that little circle, right? So maybe how does that circle change as I move along the graph? So there's my impact of a third derivative. It's the rate at which the circle, the osculating circle is changing as I go along the graph. But now I'm in 4 dimensions. I don't even know what that looks like. In 3 dimensions, I can picture changing that circle to a ball. So I could have an osculating sphere instead of an oscillating circle. But again, I'm going to have to draw a bunch. I'm going to have to bring a bunch more 3D printed stuff to look at. I'll bring my hat again. We'll need that. But that is next week. Yes, because tomorrow is more derivatives. And then second derivative stuff is next week. More questions. I got 4 more minutes on the clock. Well, what do you want? Okay, let me put up the schedule for a minute. I have a comment for you. So today, tomorrow, next week, spring break. 2 things to note. We get back from spring break. Well, that would mean your homework is due here. And the exam would be the next class period. There you go. So I apologize in advance. We're gonna have to study over break a little, or come back early enough with your brain to actually study when you get back. Do your homework before you leave. That'll be easier. Second, just like up here 2 weeks ago on Valentine's Day, I have been told that there is a potential for another teaching demonstration on this day. And if that's the case, it would be during this class time again. So when am I going to hold this question and answer day and review? I'm going to have to do it in the afternoon. Right before we leave for spring break, I'm going to stay late and give you all extra time. I would normally do that over my office hours over in the enrichment center. But right now, I'm looking at the schedule for the 7th, and the teaching demo's here, and then the meeting with the candidate is here at the end of my office hours. So I'm going to actually say that if y'all want me to do this as a class period, I'll do it here. I'll move our class to 3:30 in the afternoon. I'm still waiting for confirmation. But if that's the case, you'll get an email canceling class on the 7th and moving it to late in the afternoon. If you guys don't show, you guys don't show. I'll understand. We're going on break. I get it. But I literally have no other time to fit that in during the day if we move to this teaching demo. I'm hoping to get confirmation today. As soon as I get confirmation, y'all will get the email. Yay. I will see you all tomorrow. Have a wonderful rest of your day. Go back to Zoom, hit stop.